On a 20 amp branch circuit having several duplex receptacles, it is not necessarily a requirement for each of the receptacles to be rated at 20 amps. While using 20 amp receptacles is a common practice on a 20 amp branch circuit, the National Electrical Code or NEC permits the use of 15 amp receptacles on these circuits. However, there's a caveat. If a 15 amp receptacle is installed on a 20 amp branch circuit, it must be clearly identified as such. This is primarily to ensure users are aware of the receptacle's capacity and don't inadvertently overload it with devices that draw more than 15 amps. The rationale behind allowing 15 amp receptacles on 20 amp circuits comes down to the fact that most common household devices and appliances don't require the full 20 amps. Using 15 amp receptacles provides a cost-effective solution for general-purpose applications while still providing adequate protection for the circuit. It's important to remember that the overcurrent protection device, such as the circuit breaker, is designed to protect the entire circuit from overloads and short circuits. Whether the receptacles are rated for 15 amps or 20 amps, the breaker will trip if the total current draw exceeds 20 amps, preventing damage to the wiring and reducing the risk of fire. In scenarios where higher amperage devices are frequently used, such as power tools or certain kitchen appliances, it's generally recommended to use 20 amp receptacles to ensure a secure and reliable connection. This minimizes the risk of overheating or damage to the receptacle due to excessive current draw. Furthermore, depending on the specific application and local electrical codes, there may be additional requirements or restrictions on the type and number of receptacles allowed on a 20 amp branch circuit. Consulting with a qualified electrician is always a good idea to ensure compliance with all applicable regulations and to select the appropriate receptacles for the intended use. Consider the implications of the branch circuit's load calculations and the overall electrical system design. For example, in commercial settings or industrial facilities, the NEC may have stricter requirements for receptacle ratings and circuit configurations to accommodate the higher demands of the equipment being used. These requirements often address factors such as voltage drop, conductor ampacity, and grounding practices to ensure safe and efficient operation. Switching to the second question regarding the scenario of an extension cord with a broken ground pin that is protected by a ground fault circuit interrupter, or GFCI. A properly functioning GFCI will indeed trip if there is a break in the ground pin of an extension cord. The way a GFCI tester operates involves simulating a ground fault, which then prompts the GFCI to trip. This is a crucial safety mechanism designed to protect individuals from electrical shock hazards. When the ground pin of an extension cord is broken, it eliminates the grounding path, which is a vital safety feature. Without a proper ground, any fault current can potentially flow through a person who comes into contact with a live part of the electrical circuit, resulting in a dangerous electric shock. The GFCI is specifically designed to detect even small imbalances in current between the hot and neutral conductors. If a portion of the current is leaking to ground, which would happen in the case of a faulty appliance or damaged cord, the GFCI will quickly interrupt the circuit, typically within a fraction of a second. This rapid response time is often fast enough to prevent serious injury or even death. The GFCI tester simulates a ground fault by creating a small current leakage path from the hot conductor to ground. When the tester is plugged into the receptacle, it introduces the simulated fault, which the GFCI detects as an imbalance in current. As a result, the GFCI trips, cutting off power to the circuit and demonstrating that it is functioning correctly. It is essential to regularly test GFCIs to ensure they are working as intended. The NEC recommends testing GFCIs at least once a month, but more frequent testing may be necessary in certain environments, such as construction sites or areas with high moisture levels. To test a GFCI, simply plug in the GFCI tester and press the test button. The GFCI should trip immediately, indicating that it is functioning properly. If the GFCI does not trip, it may be faulty and should be replaced by a qualified electrician. In the case of the extension cord with a broken ground pin, the GFCI will still provide a level of protection against ground faults. However, it is important to note that the GFCI does not protect against all types of electrical hazards. For example, it will not protect against shock hazards resulting from contact with both the hot and neutral conductors simultaneously. Additionally, the GFCI relies on the presence of a functional grounding system to operate correctly. If the grounding system is compromised, such as in the case of a broken ground pin, the GFCI may not be able to detect the ground fault effectively. Therefore, it is crucial to address any issues with the grounding system promptly and to never use extension cords or other electrical equipment with damaged or missing ground pins. Extension cords should be inspected regularly for any signs of damage, such as cuts, abrasions, or exposed wires. Damaged extension cords should be repaired or replaced immediately to prevent electrical hazards. Furthermore, it's important to use the correct type of extension cord for the intended application. Heavy-duty extension cords are designed for use with high-power appliances and equipment, while lighter-duty cords are suitable for smaller devices. Using an undersized extension cord can cause overheating and potentially lead to a fire. Consider the environmental conditions in which the extension cord will be used. Outdoor extension cords are specifically designed to withstand exposure to moisture and sunlight, while indoor cords are not. Using an indoor extension cord outdoors can create a shock hazard and damage the cord. Always follow the manufacturer's instructions when using extension cords and never overload them. Overloading an extension cord can cause it to overheat and potentially start a fire. Also, avoid running extension cords under rugs or carpets, as this can trap heat and damage the cord. The importance of electrical safety in any setting cannot be overstated. Understanding the principles behind GFCI operation, grounding systems, and extension cord usage is crucial for preventing electrical accidents and ensuring a safe working environment. Regular inspection and testing of electrical equipment, combined with adherence to safety guidelines and regulations, can significantly reduce the risk of electrical shock, fire, and other hazards. It's essential to consult with a qualified electrician for any electrical work or troubleshooting. Attempting to perform electrical repairs or modifications without the proper training and knowledge can be extremely dangerous and potentially life-threatening. Electrical work should only be performed by licensed professionals who are familiar with the NEC and other applicable codes and standards. In addition to GFCIs, there are other types of safety devices that can help protect against electrical hazards, such as arc fault circuit interrupters, or SIs. SIs are designed to detect arc faults, which are dangerous electrical conditions that can cause fires. Arc faults can occur when there is a break in the insulation of a wire or when there is a loose connection. SIs work by monitoring the electrical current for unusual patterns that indicate the presence of an arc fault. If an arc fault is detected, the SI will quickly interrupt the circuit, preventing a fire from starting. SIs are typically installed in bedrooms, living rooms, and other areas where there is a high risk of fire. Grounding is a critical aspect of electrical safety. The grounding system provides a low resistance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. A properly grounded electrical system helps to prevent electrical shock hazards and protects equipment from damage. The NEC has specific requirements for grounding electrode systems, which include grounding rods, grounding plates, and metal water pipes. These electrodes must be properly connected to the building's electrical system to ensure effective grounding. Bonding is another important concept in electrical safety. Bonding refers to the process of connecting all metal parts of an electrical system together to create a continuous electrical path. This helps to equalize the voltage between different metal parts, reducing the risk of electrical shock. Bonding is typically accomplished by using bonding jumpers, which are short lengths of wire that connect metal enclosures, conduit, and other metal parts. Surge protection is also essential for protecting electronic equipment from damage caused by voltage surges. Voltage surges can occur due to lightning strikes, power outages, or other electrical disturbances. Surge protectors work by diverting excess voltage away from sensitive electronic equipment, preventing damage to internal components. There are different types of surge protectors available, including whole house surge protectors and point-of-view surge protectors. Whole house surge protectors are installed at the main electrical panel and provide protection for the entire electrical system. Point-of-use surge protectors are plugged into individual outlets and provide protection for specific devices. Regular electrical safety inspections are recommended to identify potential hazards and ensure that the electrical system is in good working order. A qualified electrician can perform a thorough inspection of the electrical system, checking for things like loose wires, damaged outlets, and overloaded circuits. Any issues identified during the inspection should be addressed promptly to prevent electrical accidents. Electrical safety training is crucial for workers who may be exposed to electrical hazards. Training should cover topics such as electrical safety procedures, the proper use of personal protective equipment, and the hazards of working near energized equipment. Workers should be trained to recognize electrical hazards and to take appropriate precautions to avoid injury. Lockout/tagout procedures are used to prevent accidental energization of equipment during maintenance or repair. Lockout/tagout involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. This ensures that the equipment remains de-energized while work is being performed, protecting workers from electrical shock. Electrical safety is a shared responsibility. Everyone should be aware of the potential hazards associated with electricity and take steps to protect themselves and others. By following safety guidelines and regulations, we can create a safer working environment and prevent electrical accidents. Remember the specific guidelines provided in the NEC, which is a comprehensive set of standards for electrical installations. It covers a wide range of topics including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is updated every 3 years to reflect changes in technology and industry practices. It is essential for electricians and other electrical professionals to stay up to date on the latest requirements of the NEC to ensure compliance with all applicable codes and standards. Understanding the requirements for overcurrent protection is crucial for electrical safety. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from overloads and short circuits. These devices will automatically trip or blow when the current exceeds the rated capacity of the circuit, preventing damage to the wiring and reducing the risk of fire. The size of the overcurrent protection device must be properly matched to the ampacity of the circuit conductors. Using an undersized overcurrent protection device can result in nuisance tripping, while using an oversized device can allow the circuit to become overloaded, potentially leading to a fire. The NEC has specific requirements for the selection and installation of overcurrent protection devices. Understanding the principles of grounding and bonding is essential for electrical safety. Grounding provides a low-resistance path for fault current to flow back to the source, allowing the overcurrent protection device to trip and de-energize the circuit. Bonding connects all metal parts of an electrical system together to create a continuous electrical path, reducing the risk of electrical shock. The NEC has specific requirements for grounding electrode systems and bonding methods. Following these requirements is crucial for ensuring a safe and effective grounding system. The importance of using the correct wiring methods for electrical installations cannot be overstated. The NEC specifies the types of wiring methods that are permitted for different applications. These wiring methods include conduit, cable, and flexible cords. Each wiring method has its own set of requirements for installation and support. Using the correct wiring method is essential for ensuring the safety and reliability of the electrical system. Proper installation of electrical equipment is crucial for electrical safety. The NEC has specific requirements for the installation of electrical equipment, such as receptacles, switches, and lighting fixtures. These requirements cover things like mounting heights, clearances, and wiring connections. Following these requirements is essential for ensuring that electrical equipment is installed safely and correctly. The hazards of working near energized electrical equipment should be understood. Working near energized equipment can be extremely dangerous and can result in serious injury or death. It is important to de-energize equipment whenever possible before performing any work. If it is not possible to energize the equipment, then appropriate precautions must be taken to protect workers from electrical shock, such as using insulated tools and wearing personal protective equipment. The use of personal protective equipment, or PPE, is essential for electrical safety. PPE includes things like insulated gloves, safety glasses, and arc-rated clothing. PPE helps to protect workers from electrical shock, burns, and other injuries. It is important to select the correct PPE for the specific task being performed and to ensure that it is in good condition. Regular inspection of electrical equipment is crucial for identifying potential hazards. Electrical equipment should be inspected regularly for things like loose wires, damaged insulation, and broken parts. Any issues identified during the inspection should be addressed promptly to prevent electrical accidents. Electrical safety training is essential for all workers who may be exposed to electrical hazards. Training should cover topics such as electrical safety procedures, the proper use of PPE, and the hazards of working near energized equipment. Workers should be trained to recognize electrical hazards and to take appropriate precautions to avoid injury. Lockout/tagout procedures are used to prevent accidental energization of equipment during maintenance or repair. Lockout/tagout involves disconnecting the equipment from its power source and placing a lock and tag on the disconnect switch to prevent it from being turned on. This ensures that the equipment remains energized while work is being performed, protecting workers from electrical shock. Electrical safety is a shared responsibility. Everyone should be aware of the potential hazards associated with electricity and take steps to protect themselves and others. By following safety guidelines and regulations, a safer working environment can be created and electrical accidents prevented.